So most of when I'm talking at you today is going to be a live coding session. We're going to take some data that I have preloaded into my laptop, and together with me typing at the keyboard, we're going to build a model, fit it, discover that the model sucks, fix the model, fit it again, it still sucks, and then some of the problems will be extending the model in various ways and thinking about the meaning of that. But before we jump into code, I just want to make sure everybody's kind of on the same page. So I'm going to write some stuff on a chalkboard. So you probably learned earlier in the week that, at least in a Bayesian sense, the fundamental probability distribution that we deal with all the time is the joint distribution of data and parameters in some model. Data we usually write as D, parameters we often write as theta. And you probably wrote that earlier in the week in a sort of before and after picture. So before I do an experiment, I have some idea about the distribution of parameters in the world. So maybe parameters here are like the slope of a bulge mass black hole mass relation. Like maybe that should be positive, bigger bulges or bigger black holes at least. Or maybe parameters here are the masses of black holes detected by LIGO. They're probably from like 5 to 100 solar masses. So let's, make up some distribution for them. Before, so this is often called the prior. And then you learn there's another function called the likelihood, which says now pretend I know exactly what the parameters of my system are. How does that translate into data that I pick up in my instrument, I observe in a telescope, whatever? Okay? But fundamentally, the thing we're working with is this very high dimensional distribution. It's the joint distribution between the two. Okay? And a program that is going to feature prominently in today's work is a programming language called Stan. And Stan is one of many domain-specific languages. The domain that it tries to handle efficiently and easily is writing down this distribution in an intelligible way. And the problem it solves for you is once you have written down this distribution in Stan, it will compile a program that will automatically Markov chain Monte Carlo sample from it. So it hides all of the details that you've been focused on earlier in the week. All you have to do is think about this distribution. Okay? So that's what we're going to be focused on today. And this distribution is a way of formalizing a model of how you got your data. Now, a model, have people heard the phrase, the map is not the territory? I wish there was the same thing with a model. Okay? A model is not really how you get your data. A model is a just so story. Okay? It's a story that you tell about how you went from parameters of some system to observed data that hopefully is accurate enough that it captures the key features of whatever instrument you're using, simple enough that you can communicate it to people and they can, believe that it's right, and efficient enough that when you plug it into your technology, like your MCMC sampler or whatnot, you can get an answer. And a lot of times these three goals come into conflict. So what we're going to do today is we're going to start by telling very simple just so stories about how we got a data set. And we're going to gradually add more bells and whistles to the just so stories as we see that they're inadequate. Okay? But it's very important to keep this in your mind. The model is not reality. The model is trying to capture some features of reality. It's too hard to get everything in the model. Does that story make sense to everybody? Okay. Great. So let's get set up. So now I'm going to start screen recording. Boom. Okay. That's magic. I didn't even know you could do that. This is fabulous. So I have here an IPython notebook. You guys are all familiar with IPython notebooks, right? You've been playing around with them for the last couple of days at least, if not longer. It has some basic boilerplate, which I put at the head of almost all. Better restart. Let's make sure we've got a fresh notebook going here. It has some basic boilerplate that I put at the head of all my notebooks that makes the plots look pretty on my high-resolution monitor. And then it has some libraries. So let's start in the middle. PyStan is the Python interface to this stan program, which is what we're going to use to write down our models and eventually sample from them. Pandas is a library for working with data in tables. You may have seen that before. Seaborn is a plotting library that makes plots look even prettier than the first line there. RViz is a library that understands MCMC samples. So it can work with stan, it can work with MC, that Dan Foreman-Mackey told you about earlier. It can work with PyMC3, which is another library that tries to do what stan does. It knows about PyTorch and a number of other libraries like this, and you can work with these samples in a unified common interface, so you don't have to worry too much about which program generated the samples. So let's bring all that stuff into our library. All right, it's all loaded. Great. Now, have you guys seen the paper by Hogg, Bovey, and Lang called Data Analysis Recipes, Fitting a Line to Data? Has everybody seen that? Okay. No, you have not. Okay. It is a fabulous paper. David Hogg talked to you on Monday. It does what it says on the tin. Okay? It is fitting a line to data. And that is the exercise that we are going to start with here. Not because we always want to fit a line in astronomy, but because it's a simple enough example that I can code it for you in front of you. We can have a meaningful discussion about why a line is a crappy model, find ways to enhance it, etc., in 45 minutes or maybe an hour without going off the deep end into real physics. Okay, so with that disclaimer, I am not encouraging you to fit lines to everything. Please don't do that. But sometimes it's what you want to fit. Unusually for this crowd, Hogg, Bovey, and Lang are usually really good. They did not release their data set. So I PDF scraped it, and here is the data set in a string in the notebook. This is like 10,000 things you should not do, okay? When you are doing things, release your data, put it in a real file. Don't check it in the repository like I did this morning. Okay, but here we go. So we've got some data. And because this example is totally divorced from physics, we have an ID, 1, 2, 3, 4, 5, 6, we have a quantity x and a quantity y, and a sigma x, a sigma y, and then a correlation coefficient. These don't mean anything, obviously, but what you might have in the back of your mind is you're in a physics lab, and let's say x is like the dial for voltage. You're poking some piece of kit, you can crank the voltage up and down. Y is the meter reading that comes out, the eventual voltage across some resistor way downstream of some black box or whatever. And sigma x and sigma y right now we should think of as measurement uncertainties. Okay? And when we start, we're going to imagine that x is our voltage dial that doesn't have a measurement uncertainty. That's actually not correct. Everything has measurement uncertainty, but we could pretend it's maybe negligible. We have a really, really nice power supply. We can just dial in whatever voltage we want. Okay, so we're going to ignore the sigma x and the correlation between sigma x and sigma y and just focus on the x, the y, and the sigma y columns. So let's just plot that. Uh-oh. There's the data set. Okay? So if you look at this, you can immediately see it's not going to be a good idea to fit a line to this. Okay? Like, what the heck? There's this point here, and there's that point there. There's that one there, and maybe this guy also is a little bit weird. But like, there's kind of a central core of points that look like they might actually follow a linear relationship between x and y. So because this paper is like 60 pages long and has many examples in it, they cleverly designed a data set that has lots of complications. One of those complications is some of this data is not like the others. Okay? Some of this is generated from a totally different process than others, and so you have outliers. Hopefully at the end of the lecture, we will build a model that can incorporate the outliers. But for right now, we want to be simple. So I happen to know that if you fit from index number 4 on, that is, start at the 5th data point, then you get a much better linear relationship. So let's do that. Oh, that's beautiful. Okay. All right. So now let's start telling a just so story about this data. The simplest just so story we can tell is the one I've been hinting at. There's a linear relationship between x and y. And the story goes something like this. If I cover that up, yeah, it's still visible over there. Good. The true value of y is the value that this parameter y would have had if I could measure it perfectly, is linearly related to the true value of x. Okay, that's a very simple story. This is an exact linear relationship. Okay, somehow there's magic physics. Maybe we really are dealing with resistors. Resistors are almost magical. They're almost perfectly linear all the time. Maybe we really are dealing with, magic physics, and there is strictly a linear relationship between these quantities. But even if we aren't, this isn't a bad place to start. Okay, so now let's write down a model. So this is how the true value of y relates to the true value of x. But we don't have, in this plot, the true value of y. We have an observed value of y. And it's subject to some measurement uncertainty. The measurement uncertainty we're going to model as a random process. It's too complicated to figure out what it is exactly. It's got some statistical distribution. So in order to specify a complete model for this data set, we need the relationship between the true values, and we also need the model of the measurement. Okay? The model of the measurement, the simplest one we could write down, is the experimenter has helpfully given us a measure of their uncertainty. So we pretend that the observed value that we see is normally distributed about the true value with the uncertainty the experimenter has given us. When I write things like this, something twiddle something else, is that notation familiar to everyone? It means this is a random variable which follows this distribution. Okay? Now, that is making a number of assumptions. This is a huge assumption, but additionally, we're assuming that the value of uncertainty that was given to us by the experimenter is right, or calibrated, or accurate somehow. We're assuming that the experiment is well controlled enough that the uncertainties might actually follow a normal distribution. We don't have a bias in these observations, for example, that shifts the peak away from the true value. We don't have weird experimental breakdowns or nonlinearities that can sometimes give extreme values in the tail for no good reason. Right? A normal distribution is very compact. Most distributions have heavier tails than that. So there's a whole bunch of assumptions built into this model. But nonetheless, it's a tractable one, it's simple, and it is often attractive for those reasons. So let's fit it. So how many people here have seen Stan before? I'm so sorry, you people will be bored. Everyone else, here's Stan. So Stan is a separate programming language to Python. It actually follows more of a C-like syntax, though of course the computations that it's doing aren't like C. You're writing down a model, and then it's going to make a whole program that does sampling. So let's get started. We'll call the program, the Stan program, linear.stan. And Stan very much behaves in this sort of before-after setup. The first thing you need to tell Stan is, what do your data look like? Because it's going to imagine you're going to feed it some data from your experiment, and then it's going to sample over these thetas conditional on the data. Okay, that's the posterior distribution that you may have learned about Monday or Tuesday. So what do our data look like? Well, we have some number of observations. And at each observation, we have an x. So we make a vector that is n obs long. We have an x, and we have a y. And we're also given some uncertainty. That kind of notation makes sense to everybody? It's just telling Stan what sort of data to expect. Next, Stan would like to know what the parameters look like. What are the parameters in this just so story that I've written down? M, definitely. B, definitely. Are there any others? What about the true value of y? I don't actually know what that is, right? It's not something that I measure. I measure the observed value of y. It's not something I know a priori, like x I know because the observer just gave me the x values, right? So that is also a parameter. If you were drawing this as a graphical model, you had graphical models yesterday? If you were drawing this as a graphical model, how do I want to do this? That's what the graphical model would look like for this, right? There's a slope and an intercept that's like some global parameter. And then we go inside this measurement box. For each measurement, there's a true value of y, which we don't get to observe, but we could predict if we knew x and m and b. So that's why those flow into there. Then from that, we observe a y, and we know what its sigma is. So now, if you were drawing it with Daft or something like that, I don't know which library you use, but you would shade that box because this is actually observed. Everything else in here is not. Does that make sense to everybody? Okay, turns out you can eliminate y true with a little bit of math. We're not going to do that. We're just going to make the sampler sample over it. It's happy to do that for us, and later on we won't be able to eliminate y true. Okay, so why get too specialized early on? So m is a real number, b is a real number, y true is a vector that's n obs large. Make sense to everybody? Okay. Oh, yes. Is that better? Yeah. Oh, yeah, thank you.
Do you have to specify the variable type of a vector? Is it just assumed to be a real value?
Because Stan is not like a full-on program, like you wouldn't write, an n-body code in Stan. It's assumed to be a vector of real numbers. Stan is not friendly, unfortunately, to complex numbers, which can make life rather difficult if you're doing something that involves the Fourier transform of something else. If you want, we can talk offline about why Stan is a big advantage. The MCMC sampler underlying it is much more sophisticated than the Metropolis Hastings samplers you've used so far. It uses the gradient of the probability to pick new moves. So it has to be able to take the derivative of this program with respect to these things. And there's a huge machinery that sits underneath Stan to do that. That's why you have to go into a special language or a restricted subset. The Python PyMC3, for example, uses Theano, which is a Python library to do this. You have to write everything inside Theano so that it can automatically calculate gradients. It's a pain, but the sampling is a huge win. You can sample, I personally have sampled from 150,000 dimensional distributions in Stan, and that's almost unthinkable with the Metropolis Hastings sampler. You just can't do it. Okay, now let's write our model. So it's on the sheet that I'm supposed to talk about priors. I may say some things about them at the very end, or maybe we can just talk about them offline in discussions. But for right now, I'm going to dodge that issue. Let's just put a flat prior on M and B. Okay? That's not necessarily what you want to do. A flat prior on M, in particular, M is the slope of the line. A flat prior that's unbounded puts an awful lot of weight at very, very large and very, very small slopes. So if you were to draw the prior that we're putting on M by leaving it flat, you would say, well, a priori, I really, really, really like lines like this, and I like lines like that, and maybe even vertical lines, and I think these lines are stupid. And, you know, that's not a physically realistic situation. However, our data set is good enough that the likelihood will dominate the prior, and we don't have to care. Okay, so I'm going to just make a note. If I don't say anything, right, a flat density is just constant. So if I don't write down anything for the density for M or B, it's just flat. Okay. What about Y true? What should I write for that? Anybody have an idea? It's determined, right? If I know M and I know B, then I just get Y true out. So in fact, even though I said it was a parameter, I'm going to move it here for a moment. Just like that. The reason I put it in a transformed parameters block rather than a parameters block is Stan doesn't actually have any freedom to pick it. In our current model, Y true is given a nice tight delta function distribution where it is exactly equal to M times X plus B. In a moment, that won't be the case. I still want Stan to remember what Y true is, and it will change as M and B change. So every MC step, when I change the slope and the intercept of the line, Y true will change. So I put it in a transform parameters block. So Stan will keep track of this for us. The only thing left, if we have all flat priors, the only thing left is the likelihood function. And we said that Y-obs should be normally distributed about Y true with uncertainty sigma Y. So let's code that up. There, done. Okay. So this is a Stan program that represents the model we just wrote. To fit it, we compile it. While it's compiling, I'm going to assemble some data to feed it. And we'll fit it. Okay? The reason that you use Stan, I apologize for the awkward silence while it's compiling, but the reason that you use Stan is once it compiles that model, right, it's ready to sample. You feed it data of the type that you told it you were going to feed it, and it will now draw samples over M and B. So now, hold on. Let's take a look at a trace plot. Did you look at these earlier when you were MCMC sampling? There we go. So this is a trace of the MCMC sampling that Stan did over the slope and the intercept. You can see here, Stan fires up 4 cores and runs 4 chains at once. They start from different places. So if they tend to get stuck in some location of parameter space, they may not all get stuck in the same place. You can see that. You can see these chains are well mixed, right? All the 4 chains overlap each other. It gives you histograms of M. If you really wanted to know what the slope was between our magical X and our magical Y, it gives the intercept B. Okay, great. Yeah.
I noticed you didn't specify anything about like how many samples. Is that calculated automatically somewhere?
It's not calculated automatically. It's set by default to be 1,000 samples. And Stan also warms up for 1,000 steps. So that's some combination of burning into the right location and then setting various sampling parameters for the first 1,000 steps, and then those are frozen and it really runs. You can change all of that by giving different arguments to the sampling. So if you need more iterations, and then maybe you want to thin the chains because you have 1,000,000 iterations, who needs a 1,000,000 element vector where everything's correlated with everything else? All of that is tunable. But for most problems, HMC, the algorithm that underlies Stan, Hamiltonian Monte Carlo, is pretty powerful. 1,000 samples gives you a reasonably good effective sample size, and you're pretty much good to go. I mean, we can check. So there's 490 effective samples in M and 460 effective samples in B out of 4,000 total. So the autocorrelation length is about 10. That's not bad. Okay, are there any questions at this point? Yeah.
Maybe I missed it, but do you have a reason to choose PyStan over PyMC3 that we saw yesterday that also uses kind of a Hamiltonian Monte Carlo?
There is no overarching principled reason to pick one or the other. I find that as long as you're dealing with like a vector of IID variables and they come from a simple common distribution, the two are about comparable. When you need to dig into the weeds and you might want to actually write like a for loop in some way, you have a vector of observations, but each one is different in some way, maybe based on some flag somewhere, etc. I find that PyMC3 struggles. It's very much like trying to do for loops in NumPy. So as long as you can express everything in a simple vectorized way, it's just as easy. I often end up in Stan because I'm writing some complicated custom distribution for my data, and I then have these various flags that go this way and that way and so on, and Stan is better for that. But they do the same thing. They have essentially the same capabilities. If you are more comfortable with PyMC3, go to town. Are there other? Yeah.
So you mentioned that the data are good enough to dominate the prior. Is there a statistic you can compute that sort of encodes the extent to which the likelihood is dominated by the data or the prior?
Yes, there is. If you take, the overall distribution is a product of these two things. What we want to know is how narrow is this in parameter space, right? So if you take and actually if you take 2 derivatives of the log of this function and then put it inside an expectation value, okay, so this is a distribution over data. You take 2 derivatives of it with respect to parameters. That's giving its curvature at some location. You calculate the expected value of that. This thing is called the Fisher information matrix. Generically, you have many parameters, so the derivatives, it's a Hessian matrix for your likelihood. That matrix contains in it, if you eigenvalue decompose it, okay, it behaves like the inverse of a covariance matrix for your data. And so if you look at its eigenvalues and eigenvectors, they will tell you the directions in parameter space and the size of the sort of typical ball of the likelihood. If those sizes are smaller by a lot than your prior widths, you're good to go. Often, this is so hard that what you actually do is you write a stand program, you simulate it, and then you just look at these posteriors and you say, well, I put in a flat prior on B and I see a peak. So clearly my data are constraining. That's the real way you do this in almost all situations. But yeah, there's a whole bunch, and there's all sorts of deep information theory. The Fisher matrix is a metric on parameter space. There are even priors that are proportional to the square root of the determinant of that there's deep differential geometry information theory connections here if you really want to go down the rabbit hole. Are there other questions? Okay. So I will say, as a piece of, practicing advice, you should always look at this plot first thing. And then I will say, this plot is a terrible way to summarize your fit. Right? What does this even mean? For one thing, a cautionary note about intercepts. This is the value of y, whatever that voltage on an output thing, when we set the input dial to 0. So if you're fitting data, let's say you're fitting the M sigma relation. So on the x-axis is bulge mass of some galaxy, and on the y-axis is black hole mass. You're trying to predict black hole masses from bulge masses. They're all in logs, log of this thing in solar masses, right? The intercept is whatever the black hole mass is when the x-axis is 0. 0 in a log means it's whatever the black hole mass would be for a galaxy of 1 solar mass. That's not really a thing. So first off, you want to think a little bit about what your model means. People often fit regressions, linear regressions, in years. So now it's like, cigarette deaths on the y-axis and years on the x-axis, and then it's like how many people died from smoking in the year Jesus was born. Also not a thing. So, you have to be a little careful, right? So just getting parameter values out is not something you want to do, or at least it's not the end of the story. It's a basic sanity check, but that's it. So now I wrote some code this morning on the train, and I pray that it works, which is this thing, which is called plot fitted line. So it's intended to consume our fit and our XY data and maybe some errors. And it will make a nice plot of the range of lines that our fit permitted against the data. So we should check, right? I mean, our just so story is that the true y is linearly related to the true x. And okay, we don't see the true y, we see the observed y, but still, let's see if this kind of holds up in theory. So I'm going to just enter that into the library, and then we're going to try it. First, I'm going to get the fit in a little bit more convenient format. Oh. There's a line. I like it. Oh, I know what I did wrong, and it was stupid. Here we go. Ha. Where? Oh, thank you. Oops, that's not a thing either. That's a thing. There we go. Okay, awesome. Hey, that's a nice linear relationship. Now, I'm going to say something every now and again. I like to make fun of my colleagues, and I don't actually mean it. Okay? If we were econometricians, we'd be done. Look, it's a linear, we're done, okay? But we're astronomers. We're going to try to be better than that. Can anybody see some problems with this? Yeah.
You're using one data point to continue the linear relationship for everything below 125?
Ooh, that is some expert level problem. I wasn't even planning to address that, but indeed you're right that this point is going to have an outsized influence on the slope, right? If you think about the lever arm here, all these guys are clumped up there. So yeah, maybe what we should be doing is picking up the phone to our observer colleagues and saying, how'd you really get that data point? Was that a cloudy night? Was it a small galaxy? What? Okay, I don't think I can constructively live code a solution to that problem, so let's set it aside, and if you want to work on that in the problem session, let's do it. Are there other problems people can see? I have one. When I look, okay, I have to jump for it. When I look at that data point, right, our observer colleagues tell us that their uncertainty about it is this. But the fitted line predicts it should be here. That's like, I don't know, 3 sigma away? Okay, fine. So, you get 3 sigma events from time to time. When I look at that data point, our observer colleagues tell us the uncertainty should be that, but it's like, oh God, it's like 5 sigma away from the line that we just fit. Is it possible that our model that says that the true value of y is literally mx plus b could be a bit deficient? I think that model is basically contradicted by the observed data. Okay? So the lesson here is you can get a perfectly good fit, the sampler runs smoothly, you get an effective sample size that looks good, you make a pretty plot, and if you don't think carefully and compare your actual data to your model's predictions for the data, you can have a completely wrong model. Okay, and I will just go out on a limb. I didn't generate this data, David Hogg did, but I will tell you that this model is wrong. Yeah.
Is there a quantitative way of telling that this model is wrong?
Yes, there is. Friday, Adam is talking about model selection, or Thursday? Friday. On Friday, you will learn about model selection, which doesn't quite answer the thing you're asking, which is how do I know this model is wrong? Instead, it says I've got 2, and which one is better? But, if you can find one that's lots better, then this one is probably wrong. So that's a big topic, and I'm not going to cover it. Yeah.
But I guess, how do you tell when you need to go out and search for another model?
That's where this is more art than science. So every such instance that I know of starts from some comparison like this in data space. Right? We're actually, those black dots are real data. This line is the prediction for the real data, and we're comparing them. And, if that's a 6-dimensional comparison, you can't put it on a plot, but you can still check. Like, you can ask, suppose you're worried that your model's doing a poor job down here. You could make up a bunch of fake dial settings from 50 to 100, and then generate, what the model thinks the output ought to be and compare to a couple of your data points there by, I don't know, looking at their difference in number of sigma or various other checks. Does that make sense? Okay. Part of the reason this is such a hard problem is all models are wrong. The map is not the territory. So, this is a hugely context-specific question, and you have to think about the scientific context you're doing your modeling in. So, I have something like 5 minutes left in the formal lecture period. I'm prepared to go a little bit over, but I'm not going to force you to sit here without coffee for that long. So let's just fix this model in one way. I can immediately think of two ways we could fix this model, and you guys can pick which direction we want to go. Can anybody imagine, like, what really is the problem? The problem is the predictions have to live right on this line, and the observations clearly do not. So how do we fix that? Any ideas? You've got your hand up? Yeah.
Basically just from the y equals mx plus b model, allow y not to be immediately constrained by m and b, but put a distribution on it.
Oh, yeah, I like the sound of that. Okay, so I'm going to denote that here plus epsilon. Epsilon is some scattery statistical uncertainty. Great. So that's option number one. Is the fancy way to call that is intrinsic scatter. Another option?
Okay. There's also the scatter on the x-axis and the
Ooh.
noise between.
Yeah, okay. That's a
the
problem.
parameters.
So I'm not going to solve that right now, but maybe we could talk about how to do that. So 3, and I'll put it in a little dash. You're right. We've assumed that the x numbers are known perfectly, but you saw that data table. They aren't.
Can you change the distribution that the y observational points are being drawn from whatever it currently is to better favor the uncertainty?
I like that. Maybe we'll code 2 of these, because I quite like that one. I'm going to call it 2A because it's kind of related. Maybe make it heavy tails, right? Because, I mean, I was implicitly doing a calculation in my head, 5 sigma never happens. But if your distribution has heavy tails, 5 sigma can happen all the time. Nobody came up. So my favorite way to change this, as a theorist, is to say that observers suck. Okay? So I think maybe we should do intrinsic scatter, and then if people are still feeling frisky without any coffee, maybe we'll do change the normal distribution to heavy tails. I will say what this would be is saying, you have to work with the people who actually generated your data, and they have a very hard job because they have some instrument that they have to control, like LSST, right? It's not a small undertaking. You need to really understand where those sigmas come from. And in many instances, the sigmas do not come with sufficient precision for what you need, right? They may come with sufficient precision for whatever was happening originally, but not for what you need. So the simple solution here would be just introduce one more parameter that's just a factor on the observational error bars and just cranks them up. And you can fit that, right? Because you can tell how much you need to expand those to make all of these consistent with that line. So you just fit that factor, and then you can call up your observer friends and be like, well, you know what? I have determined that you've underestimated your error bars by 3 plus or minus 1.5. And they love that. It's really, everyone loves to get that phone call. Okay, let's fit the intrinsic scatter. So now in the intrinsic scatter, what's happening is there's a new parameter. And I don't know what y true is just from m and b. I have to account for the fact that y true doesn't follow precisely the linear relation. It scatters around it. Okay? So let's change this. In equations, this would be a simple way to implement intrinsic scatter is that mx plus b predicts the mean value of y true, but then there's a noise in the instrument, or maybe physics we haven't modeled, or whatever, right? So let's code that up. Now we're going to do what you really shouldn't do, and we're just going to copy this file and name it something new. Okay, so now here, it really is the case that yTrue is a parameter. Its mean value is given by mx plus b. Oh, crap. Thank you. Right, that's what I wrote down before. And we have one more parameter. So I'm just casually demonstrating features of Stan to you. Things like standard deviations are always positive, right? They can't go less than 0. So we put a constraint. Sigma is a real number with a lower limit of 0. That's the intrinsic scatter. There's n obs worth of yTrues. This is now the mean value of yTrue. Okay. Let's see what happens. I wish my computer were faster. There we go. Oh, wow. Okay, so we get an M and we get a B. They're basically consistent with what we got before, but now we get to measure the intrinsic scatter, which is 30 units, whatever those are. Okay, that's the degree to which the line has to be fattened in order to match the data. Okay, does that make sense to everybody? Oops. It's hog data. This is why pair coding is such a useful thing.
It would be funny to meet a data hog one day, though.
Yeah, data hog. So now you can see the lines broadened out quite a bit. And the reason is that now there's a trade-off, right? I can make the line a little bit wrong because there's intrinsic scatter on the points around the line, right? So now I'm less certain about the slopes. Now I didn't draw on here the intrinsic scatter. I could make a new set of fat bars that are just like plus and minus 1 sigma around the line. If I had code for that, or you wanted to wait for a minute, you could see that it would now encompass everything. Okay? So now I want to take a couple of minutes and talk about one of the model extensions we have in the homework, because it is a type of extension that we see a lot in astronomy. And I'm not going to code it up, but I can show you how to code it up during the problem session if you want to, or you can take a stab at it yourself. Okay? So we've seen, how we fit this with a simple model. We extended the model a little bit, but we still are only working with data points 4 and onward. Right? We still have that bad data from early on that we haven't dealt with. right, up here, right? So these are the points that we're fitting, and there's those points out there. What could we do about that? Suppose you have a data set that looks like this, right? Your observer friends have given you a data set, or you've got one, you downloaded it from the LSST database or whatever, and it looks like that. What do we do? We better tell a different just so story, right? And we're almost there. We still have our X settings. Okay, we haven't introduced any X error. We still have our Y trues, but the just so story, we've actually already been telling it. This point, and this point, and that point, and that point, they still have a Y true. It's just not associated to their X, right? The setting of X was apparently irrelevant for some of these points, okay? The statistical model we would use in that context is called a mixture model. This data set is a mix of two things. One thing is some data points that follow a nice linear relationship where Y true is based on their X true with some intrinsic scatter. And one other thing where Y true is just some random value. Nothing to do with the settings. The apparatus broke, somebody kicked a cable, miscoded something in a data file, whatever. The way to represent that is, instead of what's written up there, to say that Y true follows a normal distribution, just like we wrote before, some fraction of the time. And the rest of the time comes from a completely different distribution. Yeah.
How do you know that it's two different models for saying, and not just, I mean, why not 3 or 4 or more?
That is a statement you have to make based on your physics judgment about how the data were actually generated. So, you know, if it's something so simple like this, you might just say, well, I've got a few outliers. You know, there's like 1, 2, 3, like there's like 4 outlier points. Maybe I don't need, right, to think too carefully. But if it's in real life and you're going to write a paper about it, you should probably sit down and think, like, is there a detector where like some piece of it can be on or off? Is there a calibration of that detector that can be good or bad? You know, how many different ways could this break? And then you might want to introduce more components here. Okay? But that, you know, in the absence of like physics content, there's no way to make that decision. Let me see if I'm still mic'd. Good, okay. So this is also easy to encode in Stan. So one of the problems is to put that into Stan. And if you're working on that problem, drag me over right away and I'll show you how to do it. But I wanted to mention this because mixture models occur very often in astronomy. We have good things and bad things in our data set, and we don't know which is which. Okay, thanks. Mm-hmm.
Right. So before you jump into the notebook, which you can grab via a Git pull, I would like to ask if there are any questions for Will right now.
So in the case of mixture model, let's say you have a point that is like if you just visually look, you're sort of not sure whether it's like part of this chunk where you fit line or it's like completely outside, right? So in that case, if I don't consider mixture model and if I just fit line, then I will get some parameters for slope and intercept. But if I introduce mixture model, then because now there is some probability that it could be like in the other normal distribution and it could be in this. So that would also affect my line parameters, right?
That's right.
So I was wondering like if, so in that case, like introducing mixture model may not be a good idea because like let's say it would be a good idea to include the whole thing in the main instead, you know what I mean? So are there like sort of constraints on like when you should use it, or like whether let's say your scatter is bigger than some value or something, like how do you decide when to use it basically?
You have to decide based on the physics that you know. So it depends, it's true, a data point that's marginal has all the data points have an effect on the slope and the intercept. So it does something to the slope and the intercept. It's marginal, so you may never know. One nice thing about a mixture model like this is it does not firmly assign any given point to good or bad. It lets them be mixed. And so if all the points are consistent with following the line, you'll find that A is very near to 1, which means this term is almost not important at all. You'll get almost the same slope you had before. So it's safe in that sense if you want to stick it in. There are fitting difficulties that can occur from that because you're no longer constraining these things because there's no data associated to that part of the model. So you have to be a little careful. You can't use flat priors anymore. But, at some level, I would say it's actually better to stick it in than leave it out in every circumstance. However, if your data look pretty good, you're safe without it.
Any further questions? All right, I have a quick question, actually. So essentially, throughout the week, everything we've done, we have made some assumption about a flat prior. So we've essentially said the possibility that anything that we're trying to infer is any value is equal at all positions.
Yep.
Can you talk just briefly about if that is essentially the choice that you always make, or if not, how would one go about making a separate choice than just the flat prior?
So I actually almost never make that in practice because it's almost never the case that we are totally agnostic about even the scale of a thing, right? Like suppose you're fitting people's heights. You're pretty sure people are not 10 to the 10 meters tall, whereas a flat prior says that's just as likely as anything else. So in this specific example, I would probably use a prior, and you can find it, Dan Foreman-Mackey wrote about it, and Jake Vanderplas actually wrote about it first, I think. I would use a prior that says, if I don't know anything else, every angle is equally likely for my line, right? It could be flat, it could be 45 degrees, it could be 90 degrees, it could, whatever. And the angle, let's call it angle alpha, not to be confused with parameters. The angle is the arctangent of M. Another way to put that is, M is the tangent of the angle. And now, maybe everybody knows how probability distributions work, and this is going to be a snooze fest, but if I want to impose the equivalent prior on M to flat in angle, then what I would say is that the prior on M is equal to the prior on angle times a Jacobian factor. These things are densities. They have units of per alpha. This has units of per M. We have to convert between the two by taking this derivative. And now that works out to something like P of alpha over, if I remember this right, 1 plus m squared. So you can see that that downweights big M's. And now if this is flat, then it's just a constant. So you just put in a sampling statement that says add the log of 1 plus m squared to the density. Or you could be fancy and you could say that m is distributed as Cauchy 0, 1. This is the Cauchy distribution, so Stan already knows about it. Okay, so I guess what I'm saying, I may use a flat prior, but I will think about what variable I want things to be flat in. If I were fitting people's heights, I might use something that's like flat to 10 feet and then decays if I want to pretend I really don't know about people's heights, et cetera, et cetera, et cetera. That makes sense to everybody? Maybe everyone's seen these sorts of transformations all the time, but I hope that was useful to go through.
All right, so we are going to, in the time that is remaining before we finish for the day, Will is going to take us through a partial solution. We're not going to do every single problem that was posed because, again, part of the idea was you could try so many different things when looking at the data and building your story, which Will will tell us which one he's going to actually solve in just a second.
Okay, so I just coded up a solution to incorporating uncertainty in the x dimension. So I took away the intrinsic scatter. Now we just have a true x, which is unknown, a true y, which is mx plus b, and then observations of x with uncertainty and observations of y with uncertainty. So let's get that going. Okay, so the data model looks like, well, now we put in a sigma x. You can see it right there. Otherwise, everything's basically the same. We still have m and b, but now we also have parameters x true, which are unknown, okay, because we don't know what they are. Because the relationship between x true and y true is perfect, Stan doesn't sample over y true. If it knows m and b and x true, we're done. So we put y true in the transform parameter block. And the model is flat, and I should have said flat in m, b, and x true. Let me change that. We had some discussions with some folks about if you don't think that your x trues could literally be absolutely anything, you could put some population model on them. That's a bit like having sort of an intrinsic scatter. Maybe you could say the x trues all come from a Gaussian, bulge masses center somewhere and scatter by some range. Or maybe they could come from a power law, or they could come from a Schechter function because you're fitting luminosities, or anything you want. You could put some distribution on them here, but I just left it flat. And then we have two observations for each data point. One is that the observed y is given by y true with that uncertainty, and the observed x is given by x true with that uncertainty. We do the usual business, so we compile the model. The data now look like our old data, but they have one additional column, which is sigma x. We have to tell them code what that is. We run a fit. We get some slopes out. It looks like nothing's gone horribly wrong. And then we make our plot. And the reason that I took off the y scatter is because, if I look by eye, this plot looks fine. Right? The model statement is that every data point lies perfectly on this line in truth, but because x was evidently measured really poorly compared to y, right? Like it's big horizontal error bars, teeny bitty y error bars. Because x was evidently measured very poorly, those points fit that line just fine. Okay, how many people tried this solution? Probably most people. I saw a lot of people who were trying to fit it with intrinsic scatter, and there were some problems that came up with that we could talk about offline, having to do with rescaling variables and so on. This is a simpler way to do it, and in fact, for this data set, it's totally adequate. If you haven't yet, I would encourage you to try the cosmology example. It literally, so, this is some fake data that some jokers made up, right? If you can permit me to call Hogg a joker. That is real data. Those are real supernova that were observed at great cost by the Pan-STARRS instrument. And when you fit it, you will discover that the Hubble constant is about 73 kilometers per second per megaparsec, and the dark energy equation of state parameter is close to -1, and omega matter is about 0.3, and you will reproduce the degeneracy between omega matter and the dark energy equation of state parameter that's seen in, real data. You'll be duplicating a real proper data analysis. And it's not super hard. X in that language is the redshift. Y is not mx plus b. I gave you a scary looking, but in the end, it's just multiplications and divisions and a couple squarings. Y is the luminosity distance, which is some complicated function of the redshift, but I wrote that down for you, and you can fit it. That one, I mean, it won't necessarily be any more insightful than what we've been doing, but the model is physical, the data are physical, and it's kind of interesting and fun to reproduce high-profile results like that in the literature. Okay, I hope this was informative and helpful. Around the rest of today and also on Friday if you want to ask questions. And I'm happy to also take emails if you have further questions or using Stan in your research and run into trouble. Thanks.